All right, exponential functions, section 3.2. So an exponential function, we know what exponents are. It's not going to be much of a surprise. So an exponential function, let me get my regular pencil out here. There we go. An exponential function is going to be a function that is of the form f of x equals a raised to the x, okay? Where a is going to be a positive number, so it can't be 0, because 0 is not a positive number, and it can't be 1. Okay. The reason is if you had the function f of x equals 1 raised to the x, it wouldn't matter what this function 1 raised to any number is going to be 1. So this would just be the function f of x equals 1, which is just a line at y equals 1. So that's not an interesting function, which is why we'd exclude a equal to 1. But that is an exponential function. F of x is equal to a of x, a raised to the x. So let's go ahead and do an example and graph an example of an exponential function. So I have this nice big graph over here, and let's talk about the function y equals 2 raised to the x, right? Or f of x equals 2 raised to the x. We're going to plug in some values and plot them on this graph. So traditional values for x, let's do -3, -2, -1, 0, 1, 2, and 3. And I'm sure there's a way for me to make nicer lines than this, but that's fine because the rustic look makes everyone happy, I'm sure. All right, there we go. So there's our x value. Our y value is 2 raised to the x. And then we're going to write the coordinate point x comma y so we can graph it on our beautiful graph. All right, so here we have 2 raised to the -3. When you're raising a number to a negative exponent, that's the same thing as raising it to the positive exponent, but the number's in the numerator and the denominator. So 1 over 2 to the positive 3. And 2 raised to the positive 3 is 8. So this is 1/8. So we have the point -3 comma 1/8. Okay, and I'm going to come over on my graph and graph that. So -3, 1/8. I mean, we're just going to kind of, you know, it's down there. It's close to 0. The next one, -2 raised to the -2. This is 1 over 2 raised to the positive 2, and that's 4. So 1 over 4. So you have -2 comma 1/4. That's going to be a little bit further up than 1/8. 2 to the -1. That's 1 over 2 to the 1. That's just 1/2. So we have -1 comma 1/2. A little bit further up there. 2 to the 0. That's not 1 over. I just got so used to 1 over. 2 to the 0. Anything to the 0 except for 0 itself is just 1. So it's 1. We have the point 0 comma 1. 2 to the 1 is just 2. So we have the point 1 comma 2. 2 to the 2 is 4. So that's the point 2 comma 4. 2 to the 3 is 8, so we have the point 3 comma 8. And if we tried to do the next one, if we tried to do 4, and we'd have 2 to the 4th, this would end up being 16, which wouldn't fit on our graph, so that's why I stopped at 3. But you can kind of see what's going on here. So I'm going to tell you that this is how it would look if you were to extend it. So we're never going to get a negative y value out of this. Nothing you can plug in for x here will make a negative y value, right? Because all you're doing, that negative is just really taking the 2 and putting it in the denominator. So it's really going to be a positive number in the end. So there's an asymptote, a horizontal asymptote here at y equals 0. And then the graph is going to climb very, very quickly. So this is the graph of y equals 2 to the x. What you would notice is even if this were 3 to the x, or 4 to the x, or 5 to the x, or 100 to the x, the shape is going to be very similar. It's going to be slow growing, and then all of a sudden it's going to get really steep. The bigger the base, so we call this number down here the base. The bigger the base, the steeper it gets, the faster it gets steep. So, you know, if you have 100x, I mean, you're going to be very, very steep here. But they're all going to have this general shape, small on the left side, big on the right side. However, let's look at the function y equals 1/2 raised to the x. So this fits within my requirements. It's a positive number. 1/2 is a positive number. It's not equal to 1. And let's make a graph for that. So making myself a beautiful graph here. I have y equals 1/2 x. And then I will write down the coordinate point so I can graph it. So with -3, we have 1 over 2 raised to the -3. If you have a fraction raised to a negative exponent, that's the same thing as just flipping the fraction and making the exponent positive. So this is 2 over 1 is just 2, so 2 raised to the 3, so that's 8. So we have the point -3, 8. -3, 8. So already we can tell this is going to be a little bit different, right? On our previous graph, it was small over here, but over here we're already a big y value. So just kind of keep that in mind. Next we have 1/2 raised to the -2. So that's 2 over 1 raised to the +2, which is 2 squared, or 4. So -2, 4. Next, 1/2 to the -1. That's 2 over 1 raised to the +1, 2 raised to the +1, which is just 2. So -1, 2. 1/2 raised to the 0. Anything raised to the 0 is just 1. So we have 0 and 1. 1/2 raised to the first power. That's just going to be 1/2. So 1, 1/2. One-half raised to the second power, so you're squaring the top and the bottom, so 1 over 2 squared, so 1 squared over 2 squared. 1 squared is 1, 2 squared is 4, so we have 2, 1/4. And then with 3, 1/2 cubed, so that's 1 cubed over 2 cubed, which is 1 over 8. So you have the point 3, 1 over 8. That's a little further down there. And the way that this graph is going to look is a little bit like this. So just kind of compare and contrast real quick. They flip, right? When your base is between 0 and 1, you're going to get a graph where it's big on the left side and small on the right side. If your base is greater than 1, so 2, 3, 4, 4.5, 5, 25, 25 and 3/4, anything greater than 1 is going to give you a graph where it's small on the left and big on the right. What you'll notice is that with both graphs, what's the same is that they both cross at 1, right? They both cross at 1, and they both have horizontal asymptotes at y equals 0. So let's go ahead and let's write down some of these important properties. So important properties of f of x equals a to the x. awful squiggly line. All right, so 1. Let's talk about the domain and range. Now, if no transformations are applied, so, right, there's just a base and an x. You don't have a +3 anywhere. There's no -2. If it's just a regular a to the x function, like the 2 that we worked on here. For the domain, you'll notice that you could plug in any number for x, right? There's no number you can't plug in for x. You could plug in -100, and you would have 1 over 2 to the 100. You'd get a number. It'd be a very, very small number. Sorry, if you had -2, you know what I'm trying to say. I'm just mixing my words up everywhere. But you could plug any x value in. Any x value is going to work. So the domain of any exponential function, and this is true even if there were transformations, is -infinity to infinity. The range. As long as your graph has not been shifted up or down, right? As long as it's there's no +5 on the outside here, -2 on the outside here, you are going to have a horizontal asymptote at y equals 0. So you're never going to touch y equals 0. And then you're going to hit every single y value going up to infinity. So your range is going to be 0 to infinity. This will change if you have a vertical shift. Let's talk a little bit about that. So if you had the function y equals 2 to the x plus 7, 2 to the x plus 7, it's going to be this same graph, except for every point is going to be shifted up 7 units. So this point right here, oh, you can't even see that. This point right here would shift up 7 units. So it goes from 1, it would go to 8. This point right here would go up 7 units. It would go to right here, right? You'd have like this. Use your imagination. And the asymptote, so this is y equals 2x plus 7. The asymptote would now be at y equals 7. So whatever this number is out here, it doesn't matter if it's plus 7 or if it were minus 5. Either way, the asymptote, the horizontal asymptote, is going to move to whatever this vertical transformation is, whatever you've shifted vertically. So if you have y equals 2 to the x minus 5, there is a horizontal asymptote at y equals 7, not 7. It's getting late, guys. -5. So domain-wise, if you have y equals 2x plus 7, sorry, my iPad just kind of shut down on me. If you have y equals 2x plus 7, the domain is no longer from 0 to infinity. The domain starts here at 7, right, where the horizontal asymptote is. So it goes from 7 to infinity. If your horizontal asymptote was down here at -5, then you would have the domain -5 to infinity. So here with 2x plus 7, just like we said, if this was 7, you'd have a graph that looked like this. And you would have the domain 7 to infinity. If you had y equals 2x minus 5, like I did on the previous page, Here at -5, you would have your horizontal asymptote, and your domain would be -5 to infinity. So the range could change, but the domain is -infinity to infinity. It's true even with transformations. So we talked about what happens if there's a vertical shift and you're trying to find the range. Let's talk about horizontal shifts, if I have any room here. So remember, a horizontal shift is going to happen inside the function. So the inside of the function for an exponential is going to be inside the exponent. So if you had y equals 2 raised to the x minus 3. So x minus 3, that whole thing is in the exponent. Remember, it's the opposite of what you think it should be. So x minus 3 actually moves the function to the right, or the graph to the right 3. This isn't going to change the domain. So if I, let's say, go back to, this is a mess. Let's go back to this one. If I did y equals 1/2 raised to the x minus 3, I would be shifting each of these points to the right 3. So this point right here, shift it 3 points over. Right? We'll do that. This point here, shift it 3 points over. This point here, shift it 3 points over. This point here, shift it 3 points over. The 3x values over. This guy, 3 over. This guy, 3 over. And this guy, 3 over. That's an awfully drawn exponential graph, but you'll notice that, okay, if I have y equals 1/2 raised to the x minus 3, if I do a horizontal shift, it doesn't change the range. You're still hitting the same y values. It's just the positioning of the graph has changed. So horizontal shifts are not going to affect your range at all. So if I just kind of draw like the original, this right here is y equals 2 to the x, and the red one is y equals 2 raised to the x minus 3. Same range. Sorry for that awkward pause there. I thought I had clicked the stop recording button, but I'm not a video editor. I'm not going to use a video editor to try to fix that, so sorry. All right, next thing. As long as we are talking about just a raised to the x, so the basic exponential function, what is going to be true is f of 0 is going to be equal to 1. So this is true no matter what the a value is. If I try this with f of x equals a to the x, plug in 0, I have a to the 0. Since a can't be 0, because 0 to the 0 is not a number, that's the only number that can't be raised to the 0, but we know a is not 0, so a is some positive number. Any number that's non-zero raised to the 0 is 1, so f of 0 is equal to 1. This is also telling us that the y-intercept is at 1. As long as you have this basic a to the x function, you have a y-intercept at 0, 1. So this is not true if you have any transformation. So if you have a left-right transformation, this won't be true. And if you have an up-down transformation, this won't be true. Or if you have a reflection, which we'll talk about in a moment, this won't be true. So it changes with transformations. So I'm going to erase this real quick so I have some room. The other thing that's true is that f of 1 is always going to be equal to a, as long as you don't have any transformations. So in the case of 2 to the x, it meant that f of 1 was equal to 2. So write down, oops, not right there, right here, f of 1 is equal to 2. So whatever your base is, f of 1 is going to be equal to that. This will change with transformations. Third property, as long as you have the base function, f of x equals a to the x, there's a horizontal asymptote, if I can write, at y equals 0. So we noticed that on both the graphs. Now, when we went to talk about domain, we talked about the fact that if you have a vertical shift, that it's going to change your horizontal asymptote. So if you have a plus 7, your horizontal asymptote would become y equals 7. If you had 2x minus 5, 2 to the x minus 5, your horizontal asymptote would be at negative 5. So if you have a vertical transformation, so a shift up or a shift down, your horizontal asymptote will shift to that number. Right, one last property to talk about. So this is our fourth property. It's that the graph is going to vary based on whether or not a is between 0 and 1 or greater than 1. So in the case where it's greater than 1, we have this shape here. So this is our 2 to the x graph. And then if it's less than 1, it's going to flip and be big on the right, or big on the left, small on the right. So the graph varies depending on whether a, which is the base, is bigger or smaller than 1. In the case that a is greater than 1, you're going to have this shape here. So this would be something like 2 to the x, 3 to the x, 5/4 raised to the x, because 5/4 is 1.25 raised to the x, so that's greater than 1. So any base that's greater than 1 is going to be small on the left, big on the right. If a is less than 1, now it still has to be greater than 0, so I'm going to write it like this, but I'm going to erase that and write it nicer. So a has to be greater than 0, and that's why I'm writing it like this. It has to be greater than 0 because that was one of the properties we talked about right away. But if it's less than 1, then it's going to flip and be big on the left and small on the right. So these would be graphs like 1/2 raised to the x, or 2/3, that's less than 1, raised to the x, or I don't know, 0.71890201 raised to the x. That would have a graph that looked like this guy over here. So depending on whether your base is a number bigger than 1 or less than 1, the shape of your graph is going to change. These are the basic and really important properties of exponential functions. All right, so let's talk about one of the last important things to talk about, and that's if there's a negative out front. Now, I told you a can't be negative. However, if you have y equals negative 2 raised to the x, I'm going to claim that a is not negative here. And I know you might say, but Mrs. Cook, there's a negative. It's right there. I don't know how you can deny that there's literally a negative there because it's there. And I understand that. But if you remember, at some point, I was having a conversation about calculators, and I told you that if you put in negative 2 squared in your calculator like this, no parentheses, that your calculator will spit out negative 4. And that your calculator is doing it correct. This is not a glitch in the calculator. This is not your calculator acting in a way that is abnormal. This is your calculator doing exactly what it's supposed to do. It says that the negative's out here, the square is only attached to the 2. So it's squaring the 2 and just keeping that negative out front. Now, if I had put parentheses here, if I had done negative 2 squared, this would tell the calculator that you wanted to take negative 2 and multiply it together with negative 2, and you would get positive 4. So this is an okay exponential function because the base isn't negative. Now, if I was trying to tell you that this was okay, we'd have a different issue, okay? We can't have y equals parenthesis negative 2 raised to the x. That would be a much different issue. I wouldn't do that because that's not something we can do with exponentials. So your base does have to be positive. But you can have a negative out front. And let's talk about what that does. So I am going to go ahead and erase, oops, that is not the eraser. I'm going to erase this for a sec. And I went to the previous slide where we had 2 to the x, and I took his table and I'm going to plop it down right here. Now, the difference we're going to have here is that there's going to be a negative here. So the number in the very end will be negative. There will be a negative here, negative here. So this would be negative 1/8, right? Negative, 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 negative 1/4. Negative, 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 negative 1/2. Negative, negative, negative. I mean, you can see where this is going, right? We're just making all these numbers negative. So let's use pink this time to graph. I'm going to go ahead and graph these points. So negative 3, negative 1/8. That's like here-ish. Negative 2, negative 1/4. That's like here. Negative 1, comma, negative 1/2. That's like here. 0, negative 1. That would be here. 1, negative 2. 2, negative 4. And 3, negative 8. And connect the dots. Bam. Beautiful. All right, so what's happened? Well, I can take you back to our original 2 to the x. So our original 2 to the x was this guy right here. Right? So close to the y, or close to the x-axis on the left side, far away from the x-axis on the right side. And it's the same here, right? It's close to the x-axis on the left side and far away on the right side. However, it's just flipped over the x-axis. Because if you remember, if you had negative f of x, this was a flip over the x-axis. So this reflect over x-axis. So this gives us something new to talk about. I'm going to paste something from a previous slide. There. So we had talked about, maybe I'll move that a little bit down, that if you have f of x equals a to the x, that these were your two options, right? We said that this would be something like 2 to the x, 3 to the x, blah, 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 blah. This would be something like 1/2 raised to the x, 2/3 raised to the x, something between 0 and 1. Let's talk about what happens. Move this, shrink this a little bit. The beauty of being on an iPad. Let's talk about what happens when instead we have f of x equals negative a to the x. So same situation, a greater than 1. Let's put a little squiggly. Let's put a little squiggly there for, good measure. Reflecting this guy over the x-axis, he reflects down like this. If a is between 0 and 1, we're taking this guy, and so if we had a negative out front, we'd take this guy and reflect him over the x-axis. Bam. That's what we'd have. There's a lot of things that are going to be, there's a lot of things in math that aren't incredibly important again, and there's some things that are. There's going to be some things in this section that you might not do again, but I can tell you one thing that's going to remain important is your knowledge of these basic transformations of exponential functions. Knowing these 4 graphs right here, and knowing what happens when you do vertical shifts with exponentials and how it affects the domain and range, those are the important skills. Horizontal shifts aren't as important. However, Alex does go into the horizontal shifts, so we will talk about the horizontal shifts, but it's the vertical shifts that are really, really important. So we're going to go ahead and do a few problems, and I really want to focus on domain and range type issues. One last thing before we leave this slide. So I kind of gave examples of what these functions would look like. So I'm going to give examples for these guys too. This would be something like -2 to the x, -3 to the x, and so on. These guys over here would be something like -1/2 raised to the x, or -2/3 raised to the x. So there's just the examples, so you have those. One last thing to talk about here is the things that happen to the range when you flip the graph over the x-axis. I'm wondering if I can kind of like arrange this so it's not trying to move stuff around so that it's, there we go. With these guys over here, as long as you don't have a vertical shift, you're going to get the range is 0 to infinity. 0 to infinity. However, when you flip your graph, this is going to change what the range is. So now the y values that are covered go from -infinity to 0, right? Because you've flipped the y values. So your range is no longer 0 to infinity, it's -infinity to 0. So just something to throw out there, how those ranges change when you add that negative out front. So let's do some examples now where we sketch some graphs. So for the next several problems, the instructions are going to be the same. For the exponential function below, find the domain, range, and horizontal asymptote, then sketch the graph of the function. So we have f of x equals -3 raised to the x. So let's just kind of start doing all the things. Domain is really nice and easy with exponentials. It's always -infinity to infinity, without exception. It will always be -infinity to infinity. For the range, it's honestly best to just draw your graph and then come back to it. I know we just did one over here, but I'm going to draw my graph before writing my range in there. For the horizontal asymptote, as long as you haven't added a number on the outside here, or subtracted, so as long as there's not a vertical shift, your horizontal asymptote is going to be at y equals 0. Right? So you still have a horizontal asymptote at y equals 0. Now the regular 3 to the x function looks something like this. This would be 3 to the x. When you put that negative out front, remember it's flipping it over the x-axis, so this is -3 to the x. And we're probably going to want to plug in some x values. On Alex, you're going to need to plug in at least 2 x values, but I'd say 3 is a more appropriate number. So we'll start with like x equals 0. If you plug in x equals 0, you're going to get y is equal to -3 to the 0. So that's negative 1. So this is the point 0, negative 1. And what you're going to notice is that the intercept ends up always being 1 unit away from that horizontal asymptote. So x equals 1, y equals negative 3 to the 1. So that's negative 3. That's the point 1, negative 3. And we'll do 2. Y equals negative 3 raised to the 2, which is negative 9. So we have 2, negative 9. Oh, goodness. And you do your best, right? You do your best to make it as beautiful as possible. So the range here, right, it goes from negative infinity all the way up to 0. We don't include 0 because there is a horizontal asymptote there. So the range is negative infinity to 0. And there's that problem. So let's look at this guy. Here we have f of x equals 2 raised to the x minus 3. And what I want to point out is that the x minus 3 is all in the exponent. If there's a minus 3 in the exponent, that's going to mean that you're shifting to the right 3. You're probably just going to end up plugging in x values for this. So you probably won't really think about it as shifting to the right, but it's worth pointing out. So domain, that's the easy one, right? That's going to be negative infinity to positive infinity. Range we will come back to. There is no vertical shifts, so the horizontal asymptote is going to remain at y equals 0. Because there's no negative sign here, that means that we are on the top part of the asymptote. So one thing to think about, if there's a negative out front, then the graph is going to, the graph of the exponential will be below the horizontal asymptote. No negative, the graph will be above the horizontal asymptote. So let me shrink this, move that down there so it's out of my way. So we are going to be above. Now we have to shift to the right. The easier way of dealing with this is to plug in numbers. Now, here's what my brain is telling me. I want to plug in numbers where I get a nice value here. On ALEX, you can plot nice numbers. So if you wanted to plot the point like, I don't know, 2,1/8. Remember, I don't know. This is like, if you wanted to plot this point where this is not a nice number here, you're going to see a button on ALEX that looks like this. If you click on this button, it'll give you a spot where you can enter 2 numbers for a coordinate point. So you could put 2 here and 1/8 here, and you could enter it. So it doesn't have to be nice numbers. You don't have to have nice numbers to graph it on ALEX. It's just, you know, if you can make it nice, that's nice. So in order to make it nice, if I can start with this number being 0, if I can make x minus 3 into 0 and then just kind of go up from there, I'm going to get nice numbers. So I'm going to start with x equals 3 because then I'm going to have 2 raised to the 0. So if I start with x equals 3, then I have y is equal to 2 raised to the 3 minus 3. So 2 raised to the 0, which is 1. So 3, 1. Over 3, up 1. And then I'm just going to go up from there. So y equals 4. Y equals 2 raised to the 4 minus 3. So that's 2 raised to the 1, which is just 2. So I have 4, 2. X equals 5. we have y equals 2 raised to the 5 minus 3. So 2 raised to the 2, which is 4. So we have the point 5, comma 4. Over 5, up 4. Okay. And if you wanted to keep going, you could keep going, but I'm just going to, try to draw the best function I can. Given that, I don't know why that random line happened. I think I accidentally turned off the setting where I'm just drawing with my Apple Pencil. So there's that. So last thing to talk about is the range. And as you can see, it starts at 0. It goes to infinity. So our range is 0 to infinity here. So as long as there's not a vertical shift and as long as there's not a negative out front, it's going to be 0 to infinity. So those left and right shifts don't affect the range at all, and they don't affect the domain either. And they don't affect the horizontal asymptote. The only thing that the left and right shifts affect is where these points get plotted. All right, let's look at an example that's a little bit more difficult. So here we have h of x equals negative 1/3 raised to the x minus 2. So there's no left or right shifts because we don't have anything going on in the exponent besides x. But there's a few things to think about here. So first of all, this negative 2 tells us where the horizontal asymptote is going to be at. So the horizontal asymptote is going to be at y equals negative 2. So negative 2. All right. And this negative out front tells me that my graph is going to be below the horizontal asymptote. And because there's not a left or right shift, I know that the y-intercept is always going to be 1 unit away from the asymptote. So if I'm below, my y-intercept is just going to be 1 unit below that horizontal asymptote at y equals negative 2. And I'm going to need another point to plot if I'm doing this on Alex. So you can choose whatever you want. Now, what you have to think about, if you choose, if we can let's go back, hold on. Let's go back to this page. We're looking at a situation where there's a negative out front and our inside value is between 0 and 1. So if you start choosing positive values over here, you're going to end up getting fractions, which is fine, but just know that you're going to get fractions. If you choose negative x values to plug in, you're going to get nicer numbers because these are the nicer y values over here. So just kind of something to think about. And maybe I'll just kind of demonstrate that. So if I do x equal to, let's put that right down here. If I do x equal to positive 1, then y is equal to negative 1/3 raised to the 1 minus 2. So you have negative 1/3 minus 2, and that's going to be negative 7/3. So we have the point 1 comma negative 7/3. That's not a very fun point to plot. But if you did x equals negative 1, instead you would have y equals negative 1/3 raised to the negative 1 minus 2. If you raise 1/3 to the negative 1, that's the same as just flipping it upside down, flipping the fraction, it's reciprocal, and then changing that exponent to a positive. So here you just have negative 3 minus 2, which is negative 5. So you'd have the point negative 1, negative 5, which is just, it's a nicer point, right? So negative 1, negative 5, that's right down there. So just going to kind of sketch it in from here. So that's a sketch of your graph. The domain, like we've said, is negative infinity to infinity. the range. All right, so the range is all those y values. So it starts at negative infinity and it goes all the way up to negative 2. So the range is negative infinity to negative 2. The horizontal asymptote, we already said, was at y equals negative 2. And that's that for this problem. All right, here's one to trick you. All right, so we have g of x equals 5 minus 1/4 x. Now, this is tricky because all of a sudden we have this constant out front. This is one you'd really be best rewriting. So the negative is attached to the 1/4 x. So this is the same thing could be written negative 1/4 x, and then this is a positive 5, so we would write plus 5. So 5 minus 1/4 raised to the x is the same as negative 1/4 raised to the x plus 5. So right away we can pull out, let's see, domain, range. The horizontal asymptote is going to be at this vertical shift, so it's at y equals 5. Right? The domain is negative infinity to infinity. There is a negative out front, which means that we will be graphing below the horizontal asymptote. There's no left or right shifts, so let me use blue here. The y-intercept is going to be 1 unit away from the horizontal asymptote, and since it's below, it's 1 unit below. And then you just need more points to plot. So you can choose whatever value you want. However, just the same situation we had over here. If this number that you have, if your base is less than 1, it's better to choose these negative x values because it's going to make things nicer. So I'm going to do x equal to negative 1. And then we get y equals negative 1/4 raised to the negative 1 plus 5. So that's negative 4 over 1 raised to the positive 1 plus 5. So negative 4 plus 5, which is just 1. So this is the point negative 1, comma 1. It should be right about there. And we can kind of just fill in the rest of this. So then the range starts at negative infinity and would go all the way up to 5. So it would go from negative infinity to 5. So we're just going to do 2 more examples of these. They're going to go pretty quickly. Domain, range, horizontal asymptote. So here we have f of x equals 3 raised to the x plus 1 minus 2. So this x plus 1 in the exponent means that we are shifting to the left one. And this negative 2 on the outside means that we shifted down 2. It also tells us where our horizontal asymptote is at. So if our vertical shift is down 2, then horizontal asymptote is at y equals negative 2. There's no negative in front, so that means that we're graphing above the above the horizontal asymptote. Because there is a shift left or right, we can't just put our y-intercept where it would normally be, which is 1 unit above. So we're going to need to plug in some x values here. Like I said, the easiest way to start is to figure out what would make the exponent 0. So negative, if you had x equal to negative 1, that would make your exponent 0. That's the easiest place to start. You could just choose any random number. It would be fine. But if you're wondering about the easy place to start would be -1 in this case, because it would make the exponent 0. In this case, you'd have y equals 3 times -1 plus 1 minus 2. So 3 to the 0 minus 2, which is, running out of space, 1 minus 2, which is -1. So this is the point -1, -1. That's right here. You need at least 2 points. And I'm just going to start going upwards. So next number would be 0. So y equals 3 raised to the 0 plus 1 minus 2. So 3 raised to the 1 minus 2. That's just 3 minus 2, which is not negative. It is +1. So this is the point 0, +1. Now you only need 2 on Alex. I'm going to do another one. I'm just going to give us 3. So y equals 3 raised to the 1 plus 1 minus 2. So 3 squared minus 2. That's 9 minus 2, which is 7. So we have the point 1, 7. And looks just like that. So domain, -infinity to infinity. The range starts at -2, and then it goes off to infinity. Those are the y values. So -2 to infinity. And to point out why it was -infinity first here, it's because you always go smallest number to biggest number, and -infinity is smaller than 5. So you would start at -infinity and go to 5. Whereas here, the smallest number is -2, the biggest number is infinity. So there's that. All right, last one of these problems, I promise. Here we have f of x equals -4 raised to the x plus 2 plus 3. There's a lot going on here, but it's cool. It's going to be awesome. So this x plus 2, that means we are shifting left 2. This plus 3 right here means we're shifting up 3. It also tells us where our horizontal asymptote is going to be. Our domain, like always, -infinity to infinity. We'll come back for the range. The horizontal asymptote is always at that vertical shift, so at y equals +3. Okay. There is a negative out front here, which means that we will be graphing below the horizontal asymptote. Let's go ahead and plug in some values. So what would make the exponent 0 would be -2. So x equals -2. So y equals -4, -2 plus 2 plus 3. So this is -4 to the 0 plus 3, -1 plus 3, which is 2. So this is the point -2, +2. That's right here. Let's do -1. So y equals -4 raised to the -1 plus 2 plus 3. So -1 plus 2 is 1, so -4 to the 1 plus 3. That's just -4 plus 3, which is -1. So this is the point -1, -1. And then let's try 0. So y equals -4 to the 0 plus 2 plus 3. We're going to run out of room here. So that's -4 squared plus 3. So -16 plus 3, -13. So this is 0, -13. We don't actually have a place for that, so that would be like down here. And our graph would look like this. For our range, we would start at negative infinity, and then we go all the way to 3. So hopefully, I mean, that's 6 different examples of graphs, so hopefully that's a little bit helpful. There's one last thing for us to talk about in this video, and then you are done listening to me talk about exponential functions for now. But this is it on the graphing part of things. So the last thing for us to talk about is a special case, a special number. So a special case. And it's for the number e, which you might argue is a letter, but I would argue that it is a number. So e is an irrational number, which means that it doesn't have a decimal that repeats itself, and it doesn't have a decimal that ends. So the decimal has no pattern and continues forever. It's approximately 2.71838, and like I said, goes on forever. You might ask where it comes from, which would be a good question, because if I tell you it's an irrational number with no pattern on the decimal and it goes on forever, you might say, well, where in the world would they even come up with that? So where does it come from? You're going to talk more about this in calculus. I can't give you everything you need right now. But if you have this expression, 1 plus 1 over n raised to the n, if you let n go to infinity, so you make n really, really, really big, if you make n go to infinity, so you make n really, 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 really big, this goes to e, right? So you'll learn more about this in calculus, smiley face, but that's where it comes from. There's a lot of things in nature that are replicated with exponentials with a base of e. So it is really important, and you're going to see it a ton in calculus. You won't see it in Math 127 at all, so you won't see it in trigonometry, but you'll see it all the time in calculus. It will not disappear. So e is called the natural base. The natural base, and y equals e raised to the x is called a natural exponential function. But it behaves just like any other exponential function. So when it comes down to it, 2.71838 is still, let me scroll back here, is still a number that's greater than 1. So y equals e to the x is going to look like this. It's a number between 2 and 3, so it's going to be somewhere between 2 to the x and 3 to the x. It'll kind of sit right in there. So it's not going to look any different. It's just that e itself is a special number, so something worth noting. To use the E button, if you're using the Casio calculator, you should see a button. You know what? I'm going to pause this. I'm going to get a picture of a Casio, and then I'm going to point to the picture of the Casio. So hold it. All right, I grabbed a screenshot of the calculator that I've recommended to everyone. So if you look right here, you'll see an E raised to a blank. So there's two options for getting E on your calculator, on this calculator. So there's this E right here, which if it's in yellow, you use the shift key. to get to that button. The other place where E is, where did you go? Oh, there he is. He's right down here in red. So you can also click alpha because it's in red. You can click alpha and this button here to get to E. But my suggestion is oftentimes you're going to want to put an exponent on E. You have, you have a problem on Alex that is going to ask you to plug stuff into your calculator. So to get to E, you're just going to click Shift, and then you'll click the LN button. We'll be talking about what LN stands for in the next section, but Shift and then the LN button will get E on your calculator. So that's all there is for this guy. Have a fantastic day, and I'll see you in another video.